exhibiting capacitance. So that begs a question. If we go back for a moment to our electronic components, electronic concepts chart, we would have a concept called capacitance. The symbol, so this is our concept. The symbol for capacitance is given as C. The symbol is a capital C, and the units of capacitance are given as farads, F-A-R-A-D-S, farads. I'll give you a little more light. Farads. And the unit symbol is farads with a capital F. And of course, we have a brief definition. And the brief definition for capacitance would be, say, 1, ability to store charge. So it's given as the ability to store charge. The name of the device is a capacitor. And what is a capacitor? A capacitor is conductive sheets separated by a special insulator called a dielectric. So in the category of insulators, what are insulators? Insulators materials that do not conduct electricity. So can you give me some examples of some materials that you encounter that do not conduct electricity? Question would go to Andrew. Give me one type of material that does not conduct electricity. We know copper does, we know steel
rubber.
does, iron, aluminum. What's that? Andrew?
Rubber.
Rubber is a good one. Excellent. And Kyle, give me another example.
Plastic.
Plastic is really good, like plastic. Yay for plastic. All right. And let's see, Pauline, can you think of another insulator? Rolando, Gabriel, Christian, I just threw that out there in general.
Glass.
Glass is an excellent insulator.
Porcelain.
Yes, your ceramics is under a general category called ceramics, which would include certainly porcelain. Okay. Okay, these are all very good examples of rubber, plastic.
Wood.
Wood is a very good insulator, sure. If somebody's holding on to a live wire, a best way to save them is get a broomstick or something and whack their hand so that you're not conducting yourself to the live wire, and the wood is not conductive. So by using the piece of wood, hopefully you can detach their hand from whatever they're holding on to that's causing them shock and injury. So yeah, these are really, really good examples of insulators. Now, we said that these are conductive sheets that are separated by a special insulator called the dielectric. Well, we're not going to use rubber. We're not going to use wood. We're not going to use glass. There also happens to be air, and there also happens to be pure water.
I was just about to ask about pure water.
Yeah, pure water is a good insulator. You won't get electrocuted with pure water, but if it's muddy water, ionized water, you're standing in that puddle and there's a live wire in the same puddle, you're toast. But pure water, you're safe. All right, so dielectric, the special type of insulators that are used in the construction of a capacitor would be some of these items. And some of these items would be plastics.
Paper, no?
And paper. Paper is an excellent one here. Let's add paper here. Paper. And paper. So plastics, you would encounter mylar as a type of plastic. Another type of plastic, tantalum, is another type of plastic material. So there's different kinds here. There's also air that's also used. And another one that's very popular is ceramics. And another one would be electrolytic. Electrolytic. And that is a paste, and often with paper. Okay. And so that being said, the capacitors that you have been given in your kits have been this guy here we talked about, and this guy here that we've talked about. So these are two examples of capacitors that you have been given. This one happens to be a ceramic capacitor, and ceramics is a very common way of building resistors. Resistors are a ceramic compound that happens to have conductive powder in there. It's like an iron dust in there, and depending upon the concentration that varies between ceramic and the conductive material will determine how much resistivity this particular fellow has. The ceramic capacitor is designed in such a way that we do have separate conductive plates in there, and they're separated by the ceramic material. So let me give you an example here. And the same thing with the electrolytic. So when we say conductive plates, I want to show you that we want to be thinking about the plates as being something like this. Here is a plate. Here is another plate. Here is another plate. And here's another plate. So let's say I show 4 plates, and I go to attach a wire onto one of these, and then I have a wire on the far end. And so these are conductive plates. And sandwiched in between the gaps would be a variety of different kinds of what type of material? What word did I use here? It's called dielectric. Everybody say dielectric?
Electric.
Dielectric. And so this particular electrolytic capacitor can be sheets and sheets and sheets of conductive material with the paste in between, and then they roll it up and put it into a little package like so, where one wire is attached to one plate on one end of the roll, and the other one is attached this way. So in your textbook, and I'll assign the appropriate pages in your textbook for you to explore this, but the textbook goes into greater detail of the construction of how and material, various materials that goes into capacitors. What I'd want to share with you at this point is how to deal with capacitors in a circuit. So capacitors in series, and then in series they would look like this. So a pair of parallel lines is the common symbol that's used for capacitors, and we would name the C1, C2, and C3. And if I have these 3 in series, suppose this one happens to be 100 microfarads. This one is 300 microfarads. And the last one happens to be 470 microfarads. So we use the micro symbol. Remember, it's kind of like a cursive U with a long leading first stroke, and a capital F for the unit of capacitance, which is expressed as farads, and the symbol is F. So C1 is identified as having a value of 100 microfarads, C2 is 300 microfarads, C3 happens to be 470 microfarads. Well, it turns out, whoops, Rebecca dropped off for a moment here. Hold on, sorry. Okay, hopefully she can come back on. Are you back on with us, Rebecca? You dropped off for a moment. Back on, yay, Rebecca's back on, good. All right. So we have 3 in series. So C total for capacitance in series is different than resistors in series. You know, resistors in series, we just add up the numbers. Capacitors in series work differently. Capacitors in series will be with the reciprocal formula. It will be 1 over C1 plus 1 over C2 plus 1 over C3. So if you're going to use reciprocal formula, I'll write this down, reciprocal formula. As we've applied reciprocal formula to parallel resistances, one thing that you can conclude for sure, CT, comma, in series, comma, must be less than lowest cap in series, period. What is my lowest value cap in series right now? Happens to be the what? The 100 microfarad capacitor. And if I go to calculate the reciprocal relationship of these 3 values, I will have a total that is less than 100 microfarads. So that you can say for sure. The capacitors in series, calculation-wise, are kind of similar to using reciprocal method for parallel. So let me key this into the calculator. I would encourage you to do so this way, 100 and your whatever you use to get to the exponent. For some of you, it is at exp. For some of you, it is second exp. For some of you, it's whatever exponent. And this will be a change sign. So for some of you, change sign, because this will be a change sign 6. So there's your 100 micro. 100 exp negative 6 is 100 micro. What do you do with that? You have to reciprocate that. X negative 1. Then you're going to add it to 300 on your calculator, exp, change sign for the negative 6, and you're going to hit the reciprocal here, and you're going to hit plus. Then you bring in the last capacitor of 470, and it will be exp, change sign, 6, and you have to reciprocate it. Then you hit equals, you hit reciprocal one more time, and you hit equals one last time. So if you go to do that keystroke sequence, and again on your own calculators, instead of the change sign being in parentheses, some of your change sign keys might be, what would they have? A plus / minus, like that, okay? So however it works on your calculator, you know that it's got a total less than 100 microfarads. So I'm going to bring in my calculator and move this over to here. Light it up, clear the display, and I will go ahead 100. I have to use a second key on mine, double E, change sign 6, reciprocal, plus 300, second double E, change sign 6, reciprocal, plus 470, second double E, change sign 6, reciprocal, equals, reciprocal, equals. So I have a number. And what is it that you all calculate? So I see Gabriel's. Oh, that's a good number, Gabriel. What is the power of 10 that you have on the very end? I can't see that. Your microphone.
-6.
-6. Very good. And Rolando, what is your power of 10 at the end?
-6.
Good. Pauline, you see a -6 as the power of 10 on yours as well? Okay, good. Looks like everybody's spot on. So yes, if I go to do all of this, I will end up with, this is going to be equal to 64.68, looks like. 68 micro and capital F for farads, okay? So are we in agreement with respect to that value? So far, so good? Good. That's how you reconcile capacitors that are in series. Capacitors in parallel are way easier. So let me show you that. Caps, I will abbreviate now, in parallel will look like this. How will they look? Okay. C1, C2, C3. All have the same values as they did previously. This was 100 microfarads. This was 300 microfarads. And this was 470 microfarads. So my C total in series will behave with a formula by simply adding them. It will be C1 plus C2 plus C3. So CT in this particular case, just simply by adding these 400 works out to be 870 microfarads, yes? Is all of the writing pretty clear for you on your screens? I know I moved the camera around several times, I'm sorry. So in series, we have this value, and in parallel, in parallel, we have this value. In series, we had this value. Let me outline a few things here. And then the formulas that we use, there's the formulas that we use. There. And here's the formula that we use here. Okay. Good with series and parallel capacitances. So far, so good. Thumbs up if you're okay with this. Good. All right, Rolando. Thumbs up. Christian,
Yes.
thumbs up. Yes, are we good with this so far? Andrew and Kyle? I see one thumbs up. Where's the other thumbs up? Cool. All right, outstanding. So this is a brief introduction into capacitors, but now with this newfound information, if you were to see capacitors in this fashion, so let's go ahead and now do this. Caps in parallel series. So if I show you this and I'm looking for C total, and here is a measuring point, here is a point A, C1, C2, point B, a tap like so, and bring this guy over to here, C3, C4. Okay. So if you were to see this, is this a parallel series circuit? Fundamentally, do we have series components here and series components here that will allow us to simplify? So knowing what we've done before, I'm still looking for CT. We'll have up here a point A. I still have a branch coming over to here, come down. I have a point B. This guy is the series relationship between these two guys put together. What kind of a label would I put on this capacitor here between point A and B? So the question goes out to Rolando. What would I call, how would I label this?
In series, so that's the reciprocal.
I would calculate it that way, but I'm looking for a label before I do any numbers because I didn't present any numbers yet.
C1 times C2. A product over sum.
Oh, you could calculate, again, we would calculate it using product over sum. I was hoping you would call this CEQ1.
Okay.
And I'm hoping that we call this CEQ2. Just like we had an REQ1, we had an REQ2, we have a CEQ1, and we have a CEQ2. Okay, very good. And how do I determine the value of CEQ1? CEQ1 was C1 in series with C2. That's a series relationship, actually, so as not to cause any confusion. We write it this way, C2. Mathematically, you are correct. We would do the reciprocal method of 1 over C1 plus 1 over C2, or we could also do C1 times C2 over C1 plus C2. We can engage product over sum as well. So whichever method we use, this plus is not an addition symbol. This simply means in series with. That's what that plus represents. We're not going to use it for addition. It means from an equation standpoint, they are in series. So let's go ahead and pop in some values here so that you can calculate. So just for simplicity, let's go ahead and make all caps is equal to, let's say, 580 microfarads. So each one of these is 580 microfarads. So if I'm going to use reciprocal method to calculate my CEQ1, And I have two of these that are 580 microfarads. So 580 microfarads, 580 microfarads. I have another 580 microfarads over here and 580 microfarads here. If I got a pair of these in series, then their equivalent must be less than that. Are you reminded of a shortcut?
Be at half, no? Like
Yeah.
1, 2?
Yeah. Are you reminded of a shortcut? We had a shortcut. Remember, back with resistors. Back with resistors. If I had back with resistors, when using reciprocal method, one shortcut was equal to something called product over sum, which is what we have over here. This is product over sum. So I'll put a little star here, put a little star here. But we also had an alternate shortcut. Alternative shortcut would be given as C, whatever that particular capacitor is, whatever value that is, will simply divide by N. So N stands for number of identical value series caps. So do I have identical series caps in here?
Yeah.
And the value's given us 580. And how many do I have in series? I have 2 in series. So what does 580 divide by 2? Isn't that 290?
290.
290. You could do that using mama's calculator between your ears, right? So let's go ahead and double check that with a scientific calculator. Let's clear. So let's go ahead and actually key in 580. I'm going to do the reciprocal method. Second exponent, -6. So that's my first 580 microfarads. I'm going to hit reciprocal. I hit plus 580. Second exponent, -6. That's my second 580 microfarad capacitor. Hit reciprocal, hit equals, hit reciprocal, and hit equals. Guess what? Don't I end up with 290 microfarads? And isn't that what we determined would be the result of the shortcut method? So this guy works out to be 290 microfarads. And by the same token, since those are the same there, this is also 290 microfarads. Are we okay with the simplification process so far? Now, the task is to bring this to a C total. So we simplified 4 capacitors down to 2 capacitors. Now we have to simplify these into a single total. So my CT right here, here's my point A, here's my point B, and right in between here will be my CT. And CT was equal to CEQ1 in parallel with CEQ2 in parallel with. That's what that symbol represents, just like this represents in series, that little plus up there. So how do I calculate capacitors in parallel? I have 290 microfarads on this side, I have 290 microfarads on this side. Use the reciprocal method on this, yes or no?
No, you just add them.
Just add them, correct. Because if you remember from our previous sheet, we had capacitors in parallel. The total for capacitors in parallel was simply adding the values. We have capacitors, they're drawn in parallel. Electrically, they're in parallel, but the total is determined by the sum. So previously, we added 100, 300, 470, gave us 870 microfarads. Here, we happen to have 290 microfarads and 290 microfarads. So guess what we ought to do? We just simply do this. My CT is going to be equal to, mathematically, 290 microfarads plus 290 microfarads, and that will give me 580 microfarads. Yes?
Yes.
Are we okay with this?
Yes.
Mm-hmm. Okay. Are you ready for series parallel with capacitors? Okay. Okay. Series parallel caps. So in this particular instance, let's go ahead and draw it this way. I am looking for C total. Could somebody mute their microphone if you're making a lot of noise near the microphone? Yeah, because there's a lot of, some kind of noise was bleeding to your microphone. So just be mindful of that. Thank you. Here's the cap. C1. Here's the cap. Here's another cap. I'm going to make this one C2, make this C3. Here's another cap. C4. C5. Here's another cap. Do C6. Sure, why not? We have 6 caps. Okay, this one's going to be 300 microfarads. This one's going to be 300 microfarads. This one's going to be 300 microfarads. This one's going to be 100 microfarads. This one's going to be, I think, okay, all right, keep it simple. This one's going to be 100 microfarads. And this is also going to be 100 microfarads. I'm looking for a C total. You are looking for a C total. So a very close friend of mine, a professor from Nigeria, Mr. Nimine, was asked by his grandma. His grandma asked him a question. The question was, how does a man eat an elephant? Elephant's a pretty big animal. Your jaw is only so big. So how does a man eat an elephant? And the answer to the question was one byte at a time. How do we solve for C total on something like this that looks rather intimidating? Hopefully it won't be by the time we finish the explanation. If you use the same method to approach this as we've done before, this is your C total. Imagine that this is also your voltage source. How do you analyze this? You go to the point farthest away, and the point farthest away is over here, and you look back at the circuit from this perspective. And let's go ahead and label this a point A. Let's go ahead and label this a point B. So what do you see when you're looking at that wire? What do you see as a relationship between some components that are on that wire? Rebecca, what do you think?
They're in series.
What's in series? Can you be more specific?
C4, C5, and C6.
Does everybody share the same observation?
Yes.
C4, 5, and 6 appear to be in series.
Right.
So if they appear to be in series, can I replace those three with a single equivalent capacitance?
Yes.
So in my redraw, and I will do this right below the first one, I'm going to redraw. I'm going to have my C1. So C1 is still there. I'm going to have a point A. My C3 is still going to be here. I will have a point B, and my C2 is still going to be here. So C2, these guys are 100 microfarads. This is 100 microfarads. This is 100 microfarads. And then over here, I can replace this. Sorry, I started drawing a resistor, didn't I? Funny guy. Okay, I'm going to replace this with a single capacitor, which we will name CEQ number 1, and this was C4 in series with C5 in series with C6. So how do you reconcile capacitors that are in series? Mathematically, what do you do? How do I determine what the value of CEQ1 should be? Question goes to Gabriel. What do you think? I have these three in series. What did we do with capacitors in series previously? What method did we use? Look at my screen.
Reciprocal formula.
My screen. Capacitors in series, which is what we had before. The formula we use is this. What was the method? What's it called? What am I pointing at? Can you see my screen? Your microphone's off.
Oh, reciprocal formula?
Reciprocal formula, correct. And so whatever these values are in series, you know that the total of these three in series must be lower than the lowest branch.
Right.
So it must be less than 300 microfarads. So could we calculate CEQ1 using reciprocal method?
100.
One method equals reciprocal. So if I use reciprocal, that would be CEQ1 would be equal to 1 over C1, 1 over C4 plus 1 over C5 plus 1 over C6. And if you use reciprocal method, yes, this gives you a value of 100 microfarads, correct?
Yeah.
Now, that's one method. Can anybody suggest an alternate method? We don't have two, so we can't use product over sum. But
Yeah.
since we're using reciprocal, was there another reciprocal shortcut we could use?
We can do CX over N.
precisely. Another reciprocal shortcut that we had talked about before would be your CEQ1 would be equal to your CX over N. N meaning the number of capacitors that share that same value. How many capacitors share the same value of 300 microfarads? So 300 microfarads divide by 3. Won't that also give you 100 microfarads? And isn't that a faster method of determining what this value is? So this works out to be 100 microfarads for CEQ1. Is everybody okay? You can always rely on reciprocal method when these guys are in series, or you can, if they happen to be the same, let's go ahead and use the shortcut. So good job there. Thank you, Rebecca. Any questions on this so far? Now, we have taken 6 capacitors and brought it down to 4. Our viewpoint is still from this perspective, looking at this corner, and we happen to see a capacitor here. And what is the capacitor CEQ1? What is its relationship with C3?
Parallel.
They look like they're in parallel. So could we combine these into another equivalent capacitance?
Yep.
And when you go to do so, let's go ahead and bring in my tap here and bring this guy here. This guy comes here. So my points A and B here are found A and B over here. My capacitor here at this point, just like I had a capacitor over here, and we darken that, make it a little easier to see. This will be CEQ number 2. And CEQ number 2 was equal to C3 in parallel with CEQ number 1. So that means this is equal to 100 microfarads in parallel with 100 microfarads. The other parts of our circuit are the same. C1 is still 100 microfarads. And C2 is still 100 microfarads. So the question becomes, what does this calculate to become? How do I calculate capacitors that are in parallel? What was the formula method that we employed earlier?
Addition.
Yes, because if we go back to our first diagram, capacitors that are in parallel, it shows them in parallel, the total for them in parallel was to use a simple addition. We add those values together. So previously we added 100, 300, 470, gave us 870 microfarads for them being in parallel. We should be able to do the same here. We have 100 in parallel with 100. So all we have to do mathematically is 100 microfarads plus 100 microfarads gives us 200 microfarads is equal to CEQ number 2. Are we all in agreement with that so far? Okay, so this is 200 microfarads. Okay, do we have, are we okay with this so far? Are there any questions so far? All right, so the next thing becomes, what do we do to calculate a CT? Because we're still ultimately, we're looking for C total. So C total shows what relationship between these 3 capacitors. C total is equal to C1 in series with C2 in series with C3. So mathematically, how do we reconcile values that are in series for capacitors? What did we do for series capacitance before? Capacitors in series, as shown here. We used what formula? Reciprocal formula. So if we're using reciprocal formula, let's go ahead and calculate the reciprocal of these three values. So this would be equal to, since I happen to have no more space at the bottom of my paper, oh, I can do it. So you can do it. All right, so CT is equal to 100 EXP negative 6 reciprocal, and we're going to add that to 200, do this in sequence, 200 EXP negative 6 and reciprocal, and plus 100 EXP, change sign, 6 reciprocal equals, hit reciprocal one more time, and hit equals one last time. So if you follow on your calculators the appropriate keys to give you the sequence, then the result should work out to be the reciprocal plus 200. Okay, I've got a number. Good, okay, cool. So 100 recip plus 100 recip plus 200 recip. Really? Rolando? 100, 100, 200. I don't think I get the same number as you do. Rebecca, do you have a number yet? That's very good. Gabriel, Pauline, do you have a number yet? Gabriel, that looks really good. Rolando, you want to recalculate, please? Pauline, Christian, what do you have?
I got 40 microfarads.
Okay, Andrew and Kyle. Can you show me on your calculator what you have?
We're working on it.
Okay. Yeah, Rolando, your first number was in need of adjustment. Your first calculation was in need of adjustment. So the CT, long and short of it, the CT works out to be 40 microfarads for C total. Okay, by the time we're all done. Okay. And Rolando, were you able to recalculate that? Pauline, how are you coming along with that calculation? Yeah, kind of. Does it say 40? Yeah, there. Okay, I can see it now. Thank you. Yeah, it's just catching the glare off your screen. So it was, I'm looking at glare. I couldn't see any numbers. All right, Andrew and Kyle.
Almost there.
Almost there.
Almost
Okay.
there.
Yeah, whichever method is specific on your calculators to get this done, this is the method. So to summarize, this is an example of resolving series parallel capacitors, their relationships based on the initial formulas. So again, so to summarize, capacitors are those devices that exhibit a property known as capacitance. The concept is capacitance, the symbol is C, units are farads, symbol is F, ability to store charge. The device that gives us this characteristic is called a capacitor. Conductive sheets separated by special insulator called a what? Dielectric. Insulator materials, we talk about a variety of different
I just
kinds,
didn't know
but very specific kinds of capacitor insulator materials that are used as dielectrics would be these: mylar, tantalum, air, any type of ceramics, electrolytic paste. The example of the conductive plates here, your book actually does a much better illustration of all of this. Now, what your book doesn't do is show you the next two pages. And the next two pages in our notes today are capacitors in series, capacitors in parallel. So for capacitors in series, they behave in series to calculate a total that is like parallel resistors. We use the reciprocal method. So whenever you see capacitors in series, whatever their total works out to be less than the lowest cap value. And it says so here, CT in series must be less than the lowest cap in series. And we worked out the keystroke sequence for you in our notes all the way through for this particular sequence. And then capacitors in parallel, we draw them in parallel, we use the same values. The formula is as if they were resistors in series. We use the summing method, C1 plus C2 plus C3. These add up to give us 870. The first combination circuit we encountered was caps in parallel series. And if they are in series here and they are in series here, remember we use the reciprocal method. An alternate.
This has a lot more power.
I'm sorry, what's that?
Oh no, Kyle and I, we got our math problems. We got it for you.
Oh, okay, let's take a look. Yes, and hold it with a little less glare. Okay, I can see them. Perfect. Good job, guys. Nice, nice. I'm glad you were able to get those. Thank you so much. So back to our notes. If I have caps in series, we use reciprocal method, but we also happen to have reciprocal method engages a shortcut known as product over sum. So if we use 580 times 580 over 580 plus 580, we'll end up with the same value. If we use reciprocal, we'll end up with the same value. But interestingly, since these happen to be identical values, we can use a fast shortcut, which takes identical value components and divide by the number of those components. So 580 divide by 2 that have the 580 value gave us 290. These resolve to be a pair in parallel at 290, and parallel capacitors you simply add. That gives us a C total of 580 microfarads. Then if we go on to the last discussion of capacitors, capacitors in series parallel arrangements, and this one we really did something quite a bit more elaborate, which I'm glad we were able to do. Simplified 6 capacitors down to 4 capacitors down to 3 capacitors, ultimately to a single total value. And the methods were as explained. So I'm glad you were able to get all the way to here. Whew, okay, that's a full session, my friends.